When we think about the energy transfer that can occur when we plug in a light bulb, you might understand that electrical energy is being delivered to here, the filament of this incandescent light bulb, and it is changing. It's changing to light that is radiating away in this room. Now, what you may not realise is that this is also producing some other types of energy transfer. I can feel here that this is also giving off some infrared radiation that I feel as heat. Now, if I was to look at the total amount of electrical power that this was using, it says it is 41 watts. Now that means 41 joules every single second are coming into this filament light bulb. But how much of that is being used to produce the light, and how much of that is being wasted? So here I have two different types of bulb. The one on the left is the incandescent bulb that is running at about 40 watts. The one on the right is a fluorescent bulb, an energy-saving light bulb. Now they are both producing about the same amount of light. That means that the amount of energy being transferred in the form of light is about the same. However, the reading on this power meter is showing that this is about 7 watts, whereas that was about 40 watts. So if they're both producing the same amount of light, then what is that doing with all of the rest of the energy? In fact, about 3/4 of the energy in the incandescent light bulb is being turned into something else. Well, I can demonstrate exactly what. If we look at the infrared camera, then what we can see is the fluorescent light bulb is about 40 degrees, whereas the other light bulb is about 112 degrees. And this basically means that the incandescent light bulb is wasting a large amount of the energy as heat. For us to understand this, it would help for us to draw a diagram showing how the energy is being used. So how could we represent it? Well, we could represent it with a Sankey diagram. So we have two sources of light, and they are here. This one was about 40 watts going in, and this one was about 7 watts going in. I'm going to approximate this and say this was 40 and this was 10, just to make our diagrams clearer. Now, I'm going to draw a Sankey diagram with both of these to scale, and I want to show you how they look. So first of all, I want to draw the Sankey diagram of the incandescent light bulb. Now I know that 40 joules of energy was going in the form of electrical energy every single second. So I've measured here 40 centimetres, because this is going to be 40 joules of electrical energy going in. And I need to just extend it along a little bit. Now this, how far along I go, does not matter. It's entirely, I shouldn't have drawn it so high, it's entirely up to you. It doesn't mean anything however long this is. You just need to give yourself a bit of space. Now in this particular case, about 5 joules of the 40 joules was being usefully transferred into the form of light energy. So what I want to do with this diagram is represent all of the useful energy as going straight across, and all of the wasted energy is going down. So going straight across, I want 5 joules worth of energy. Now 5 centimetres is about that much. So I'm going to just continue my lines on a little bit. this, and I'm going to do it like this. Now, you might think, what's going on? Well, I'll show you exactly what's going on. We need to draw part of this arrow coming downwards. How much is going to come down? 35 joules has got to come down. So that's going to be 35 centimetres on my scale. And I'm going to start it by starting back here, from about there to about there. That's 35 coming down. And so that's going to come down like this. Then go up there like that. I'm just going to rub off that bit there because we don't need that bit. And then I need to make this into an arrowhead. The size of this arrowhead doesn't mean anything, it's just to indicate the direction of the energy flow. And now I need to label it. So 5 joules light energy coming out usefully. And here, 35 joules of heat energy wasted. So that is useful up there. I could use this to find out the efficiency. I could do the useful energy output divided by the total energy input, 5 divided by 40 times 100, and that would equal 1/8, which is about 12.5%, or something like that. I can't remember off the top of my head, 12.5% or something similar to that. So this is not very efficient because most of the energy is coming downwards. It is mostly wasted energy. Now, if I was to draw the fluorescent light bulb, well, drawing it to the same scale, I would end up drawing 10 joules coming in. So here's 10 joules coming in. And say, for example, it was producing 5 joules usefully, then it's going to be 5 across like before. And if it's 10 joules coming in, is the electrical energy in. Then if it's 5 joules usefully used, it's going to have to be 5 joules wasted, so that all 10 of those joules are spent somewhere. So let's just add them here. 5 joules, it's going to come down like this. And what I can do like that. So 5 joules of light energy that is useful, and perhaps 5 joules wasted. You can see that this would be 50% efficient because 5 is half of 10. But what you can see is, to start with, these have both got the same amount of output light. That's why both bulbs seem as bright as each other. But this one is wasting far less. It means to run this fluorescent light bulb, I don't have to put in as much energy to start with. That is why it is much smaller. And so we say that this is more efficient. You can see that 5 divided by 10 times 100 is not 100, is 50%. And that's why it's called an energy efficient light bulb. Now these Sankey diagrams, they don't have to be drawn exactly like this, because what I could draw is I could draw this scaled up to the same scale as that. It doesn't actually matter how big the diagram is. They can be drawn to scale just to represent the efficiency. For example, if I freehand sketched a Sankey diagram that looked like this, you would know that was very efficient. And if my diagram looked like this, you would know that's not very efficient at all. It's the relative proportions of the arrows that's important for gauging the efficiency, whereas it is the absolute size of the arrows that is important for understanding the total amount of energy your appliance uses. Now, it is possible that multiple things down here are your energy wasted. For example, if your thing gives off sound as well as heat, then that could be like this. For example, this one here could be the Sankey diagram of a motor car with the kinetic energy increase over here, and down here it would be sound and heat, etc. So Sankey diagrams offer us a way of understanding, first of all, just how much energy we need to run our appliances. Second of all, by looking at the sizes of those arrows, enables us to work out just how efficient an object or an appliance is just by looking at it.